In this video, we're going to look at static electricity and how something can build up a charge, whether it's by an excess amount of electrons or a deficit of electrons and have more protons of a positive charge, and what having a charge does to the forces that something might experience through static electricity. So to start us off, let's look at a little simulation here. We can rub a balloon on a sweater, and you can do this in real life as well, and you'll see that that balloon picks up lots of extra electrons. And in the process, the balloon becomes very negatively charged, while the sweater becomes positively charged because those electrons have been removed from the sweater. There is something called the triboelectric series that we're not going to have to worry too much about in this class, but it helps predict if something is going to be more likely to gain electrons or lose electrons in this rubbing interaction. In this case, a balloon is much more likely to gain electrons, and a sweater or rabbit fur or your hair might be much more likely to lose electrons. And in the process here, we see a charge being built up on both sides. Well, the reason that this is building up a charge is the protons and neutrons, those are buried very deep inside the nucleus, and they cannot be easily touched. Basically, they are not going to be scraped off in the same way that electrons can be. So here is a Bohr model of an atom being drawn, showing the electrons on the outside. In reality, those electrons are much, much farther away from the nucleus than this model is not drawn to scale. And those electrons are very easily lost or gained. You can see this in terms of electricity, electrons flowing down a conductor. But you can also see it here with static electricity, where the electrons can be gained or removed from the system physically by scraping them off. Now, there are three main ways that an object can become charged. The first one is that physical scraping, in this case, friction, creating this charge that's happening. We saw it with a balloon on the sweater. You can also see it here with John Travoltage rubbing his foot on the carpet on a nice, cold, dry day in the winter. You might experience this as well. If you have like rubber soled um, slippers that you could kind of scrape across the carpet, you might be able to pick up a static charge, and those electrons are gained from the carpeting, and then they spread out in his body. And in this case, they spread out until they have another place to go, and then they are discharged through that door handle, that conductor there. That is called grounding. It's providing extra space for the electrons that spread out into the ground, into the earth. And in that case, there's that discharge, that little shock um, that happens there on his finger. Another way that objects can become charged is through contact. Here I have two objects. An object that has a charge of -4 here, more electrons than protons. An object here where there's the same number of protons and electrons. This charge is 0. Well, if this charge object comes into contact with the uncharged object, the neutral object, that charge is given an opportunity to spread out. Now, this is obviously a huge simplification. There's obviously more atoms, more electrons, and more protons than is being shown in this diagram. But if there is contact, and these are both conductors allowing electrons to flow and spread out freely, these extra electrons are going to spread out to be more evenly distributed among the whole system now that they are connected. And if I were to remove them and separate them now, I would see that this rectangle has a charge of -1. There's still more electrons than protons, just not as big of a charge as before. And now this circle has a charge of -3. More electrons than protons. We see through contact that charge is allowed to spread out. And then our final way that we can charge objects is through induction. A good example of induction is to look back at this PhET simulation. Notice what happens when the balloon is brought over to the wall. Um, Even before it touches the wall, notice how bringing it closer to the wall started to affect the electrons in the wall. The electrons in the wall, they redistributed and they moved away from this really negative source in the balloon. And in the process created this local area next to the balloon that was very positive. Again, notice how the protons aren't moving here. The protons aren't being attracted and getting closer to the balloon because the protons are stuck with the atoms inside the wall. That'd be like the wall melting toward the balloon. Instead, it's just redistributing those electrons so that they are redistributed within that space and creating a local positive. We can see this in a similar example to what we looked at for contact. Here we have a charge on this object that's neutral. There's no charge at all. The same number of protons as electrons. If I bring a really charged object like this negative rectangle here close to that circle, well, the circle is still going to have the same number of protons and electrons. They're not going to get off of that uh, system. Instead, they just redistribute. Those electrons move away from that negatively charged object, and you have what's kind of this bipole that toward that negative is a positive portion of the circle, and then away from it is a negatively charged portion of that circle. In charging by induction, we can do a couple of different things. You could do a similar sort of demonstration with a pie pan and a styrofoam plate. So here you can charge up a foam plate, put a pie pan on top, and in the process, the electrons in the pie pan get moved up to the top, and you can discharge them, create a path to ground, which then leaves an overall negative charge in that pie pan and create this charging by induction. So, however you charge these objects, it is important to understand the effects of what can happen. Now, what we're going to care about here primarily in this unit isn't necessarily how these objects received their charge, but it's what happens afterward. So, here I've got two opposite charges, a proton and an electron, or an electron and a proton, and they are always going to attract. That's how the electrons are set to kind of orbit in this orbital cloud or this electron cloud around the nucleus. It's the negative electrons being attracted to that positive nucleus. Light charges, however, two protons or two electrons, they want to repel. And we saw that a little bit with the sweater and the balloon. We saw that if they were opposite charges, they would attract. And then likewise, if they were negative, they would repel, push away from each other. Well, we can quantify this, and we're going to start doing that here a little bit more with numbers. But first, let's just look at a couple different properties. If I take two protons, put them next to each other, and I take those same two protons and I put them next to each other just twice as far away, we know that the pair that is closer together is going to experience more electrostatic force. They're going to repel more because they have a smaller distance. And it's just like if you had two magnets. If you put two magnets really close together, you're going to feel a stronger pull between those magnets than if they were a greater distance apart. So, one thing that impacts their force is their distance, their separation. Another factor on their force is how much charge there is. If there is an overall larger charge on an object, it makes it more powerful in inducing this sort of electrostatic force. So if I have two charges here, we'll talk about this unit of microcoulombs later, but two charges both with a separation of r, so the same separation distance, but one of them has a larger charge involved. Well, that's going to have the larger electrostatic force because a greater charge is going to result in a greater force. Now, the amount of impact is different for these different variables. So, to understand that, let's look at this relationship. This is known as Coulomb's law, and it's talking about the force of attraction or repulsion and how it's related to the charge of the objects and the separation distance. You should be familiar with the different symbols and units associated here. So, electrostatic force, we're going to call that capital F, and we'll still use newtons, just like we did whenever we talked about forces earlier on in physics. And when we're talking about the charge of these objects, whether they're positive or negative, we're going to give them the symbol Q. Q1 for the object 1 charge and Q2 for the object 2 charge. Both these charges are presented with units of coulombs, um, similar to what we saw when we talked about charges going through a wire, still measured in coulombs. And we can talk about the Coulomb charge for one electron, or the Coulomb charge built up on the balloon. Um, for many, many different electrons. And then the final variable here that you need to know is the separation distance, that is r. This isn't the radius, it's the distance that's actually between these two charges. And we'll measure it center to center usually. Um, Separation distance here is in units of meters. You'll notice though there's one other um, symbol that's in here, one other variable, and it's k, lowercase k. This is actually a constant. We call this Coulomb's constant. And Coulomb's constant has kind of weird units, and we can prove those units because we know the units of everything else. So this is a good example to practice our unit analysis with. First, we can solve this whole thing for k if we wanted to find the units of k. So rearranging this, multiply both sides by r squared and divide both sides by q1, q2, we get k is equal to fr squared divided by q1 times q2. Then we can plug in units that we just found for these different things instead of the variables. So instead of force, we'll put newtons. Instead of radius or distance, we'll put meters. And then for each of the charges, those are in coulombs. And then we can simplify a little bit. These coulombs can be combined into coulomb squared. And since they're on the bottom, we can give it a negative exponent. So we can say nm squared c to the minus 2. This is our weird, crazy unit for Coulomb's constant. Coulomb's constant is 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. This will be given to you in your data booklet, and we can see that showing up here. First, in subtopic 5.1, electric fields, this equation shows up, Coulomb's law. F is equal to K Q1 Q2 over R squared. And then in our list of different constants, you'll see Coulomb constant K showing up here, 8.99 times 10 to the ninth Newton meter squared per Coulomb squared. So with this relationship, we're not going to put actual numbers that we're calculating a force in newtons yet, but we can better understand the math involved here and how these different properties relate. If I take this one and I say, okay, I doubled the distance. We said before that the closer you were, the more the force is going to be. So if here at a separation distance of r, we have a force of 4 newtons, there would be a force of 4 newtons acting on both of them. But we'll just look at this one, the rightmost positive charge is experiencing a rightward force of 4 newtons. I know that doubling the distance should decrease that force. Well, to understand exactly how much it decreases, we can look at Coulomb's law. Coulomb's law here is K times Q1, Q2 over R squared. Well, now it's instead of R squared, it's 2R squared. If I do that, notice that this 2R gets squared, so that turns into 4 times R squared. That means that we're going to be dividing this overall by an extra 4. So 4 newtons will go all the way down to 1 newton in this process. So doubling the distance cuts the force by 2 squared. If I triple the distance, it would cut the force by 3 squared, or 9. If I look back at this scenario, where I doubled one of the charges, I know that if I've increased the charge that's happening in there, I keep the distance the same, I expect that this force is going to go up. Well, how much does it go up? I am only doubling one of the charges, so this basically turns into k times q2 times q1, because twice that first charge, times q2 over r squared. None of that changes, which means that my force should be twice as big as it was before. So doubling one of the charges will double the force. All right, so here's a scenario that's been simplified a little bit. I've got 2 plus 1 charges that are a distance d apart, and then 2 plus 2 charges that are a distance 2d apart. Which pair has the greater electrostatic force? Well, notice now I am changing multiple variables. I am changing each of the charges, and I'm changing that separation distance. I'm doubling everything. Well, if I double everything, it turns into this. F is equal to k times 2q1 times 2q2 divided by 2r squared. Well, simplifying all of that, these 2's can be multiplied, and this 2 is squared, so that turns into 4q1, q2 divided by 4r squared, which is exactly the same as k times q1, q2 over r squared. So doubling everything, doubling each charge and doubling the distance results in exactly the same force. So there are a couple different factors that are presenting themselves, but you should know some different ways that charge can build up an object, whether it's friction, rubbing electrons from one material to another, whether it's through contact, touching and letting those electrons spread out, or through induction, bringing a charged object close by so that the charges can rearrange in another object. Once they have a charge, though, you need to know how you can relate the force, either repulsion or attraction, of those two objects based on Coulomb's law.